Hello everyone. So in today's session, we are going to do the problem solving on clustering and principal component analysis. This is the last session of the course. So previously we have done problem solving on supervised learning algorithms, which is linear regression and logistic regression. The difference there was that we had target attribute, that is we had label data. But in unsupervised learning, we won't have any label data. It's just that we will have some attributes. So let's start off with clustering. Let's take a text column and say clustering. Okay. Now, where did we import linear regression from? We imported it from sklearn.linear model. Where did we import logistic regression from? We imported it from, again, sklearn.linear model. Where did we import train test split from? We imported it from sklearn.model selection. Where did we import standard scalar from? We imported it from sklearn.preprocessing. So now, where are we going to import k-means from? Since we are going to do the partitional clustering, which is the variety of partitional clustering that we are doing is k-means. We've already discussed this. So we are going to import it from sklearn.cluster. And then we import k-means. Okay, so this is how we import our k-means, and this is basically going to do the k-means algorithm for us. And here we have to provide the number of clusters. So by default, the number of clusters is 8, but you can set it to any value that you want. So for now, let's set it to maybe let's say 6, and then we find the optimal value of k using the elbow method. So I'll write this as k-means. So basically this is the variable in which I'm storing my k-means. And instead of writing it like this n clusters, you can just write it as 6 also. That will also work. So basically the default value is 8, but you can set any value. It is basically the number of clusters to form as well as the number of centroids to generate. Now, if you see your DF has gender, SSCP, SSCB, HSCP, and so on till status and salary. Now, all of these are going to be attributes for us, and basically we are going to take all these records, which are how many? 205 records, and we will divide these students into 6 categories. Okay. So, if you see, the data is not standardized. Do we need standardization? Yes, we do, because here we are calculating the distances. We're calculating the Euclidean distances, and it's important that all the features are almost on the same scale. Okay, so that's why we are going to first do the standardization on our data. So where do we import our standard scalar from? We discussed from sklearn.preprocessing import standard scalar, and then you instantiate your standard scalar. Okay. Now, in standard scalar, there are two methods that we've already discussed: the fit function and the transform. So fit basically finds for every column, it finds the mu and the sigma, and the transform function is going to do the transform, that is x minus mu by sigma. So now we have to do the standardization on the entire data that we have. So can we do it directly? Yes. So sc dot fit transform, and you just provide your df here. It will give you a 2D array, right? It will give you a 2D array. It has done the standardization. But let's say we want to convert it into the data frame back. We want it to look like the data frame. Okay, so can we do that? Yes, we can. Basically, this 2D array can be converted into the data frame. Let's see how we do that. So let's say scaled df is equals to, basically you create a new data frame, and the array that you have to convert the data frame into is basically your this array. This array has to be converted into data frame, right? So let's see. Let's put it here. Let me just remove it first and see how does this look like. So it looks like this, but then the column names are gone. Can you get the column names back? Yes, we can. We can write columns is equals to, it is basically all the columns that we have, the column names that we have for our DF. So now you see, we have the data which is standardized and our column names are also there. Now this can be written as scaled DF. So this is now our scaled DF which we are going to use in clustering. Okay. So now we have already called our k-means and we have set the number of clusters to be 6. Now what should we do? Now we should build the model, right? So what we need to do is we need to call our k-means and then build the model, and generally building of the model is done by fit function. So now what do we give here? We give our scaled df, right? And now it's going to build the model for us and basically give us 6 clusters, right? And now if you want to make the predictions, now if you want to see which point is going to which cluster, you actually do the predict method. So predict method is just going to tell us which point is going to which cluster. Okay. And again, we give the scale df because we want for every point it is belonging to which cluster. Now, since we gave the number of clusters to be 6, so we will get the values 0, 1, 2, 3, 4, 5. If our number of clusters is 6, then we have the cluster names to be 0, 1, 2, 3, 4, 5. So these are the 6 clusters that we have. So basically this tells that the first point belongs to the cluster 4, the second point belongs to cluster 2, the third point belongs to cluster 1, the fourth point belongs to cluster 3, and so on. If there are 7 clusters, then the cluster numbers would be 0, 1, 2, 3, 4, 5, 6. Okay, now maybe let's put this as a column. So in our scale df, let's create one column which is clusters. Okay, and basically it will be this thing. So now if you see your scale df, you see there is one more column that is created and it basically tells us that which cluster the point belongs to. So now we have divided the data into 6 clusters. So this is how we do clustering. That is, first we build a model using the fit method and then we figure out which point belongs to which cluster. That's all about clustering. That's the algorithm and this is only the thing that we need to do in sklearn. Also remember, your DF hasn't changed. It is still the same. There's no change at all. It is not even standardized, right? Now this we did with k value as 6. And how do we evaluate our clustering? We do it by the function, not the function, the attribute inertia. If you see, let me in dot and let's do control space and we have inertia. So this is basically the inertia that we get, right? This is the inertia that we have. Now, here what we did was we figured out that we just told that k is equals to 6. Let's try to now figure out what is the optimal value of k. Let's do it by the elbow method. That is, we are going to create a graph between inertia and the number of clusters. Inertia should be less, but the number of clusters should also not be very high, because if the number of clusters are high, the problem is that the complexity of the model increases. So the number of clusters should also be low and inertia should also be low. So the graph somehow looks like this and we need to take the elbow points. That will be the optimal number of clusters. Okay, let's see. So first of all, let's revise the range, which is basically if you say for I in range 1 to 10. And let's just say we're going to print I. So what would happen? Basically, one I value will be printed as 1, 2, 3, 4, 5, 6, 7, 8, 9. So the initial point, the start point is included and the stop point is not included. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now let's write it as 11. So basically, we will have the I values from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now let's say we are trying to find the optimal number of clusters, and we say that the number of clusters can only be between the optimal number of clusters can only be between 1 to 10. You can say it to be 1 to 20 also. It's totally up to you. It's just that we don't want to increase the number of clusters, because if we increase the number of clusters, the complexity is going to be very, very high. So let's try to do it for maybe, let's say, 1 to 16. That is, from I will go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Now in this, what do? We basically do the k-means for all the I values. And let's create a list, say inertia. It's right now an empty list. And this is how I create the empty list. And now what I will do is I'm going to basically call k-means for all I values. That is, k means when the number of cluster is 1, when the number of cluster is 2, when the number of cluster is 3, and so on till 15. So k means, and here you will provide your I. And you can again store it in the variable which is k means. And then what do? You do the fit. You do the fit and provide your scale df. Okay. Now the problem is that your scale df already has one column which is clusters, which needs to be removed. So let's say scale df dot drop. Let me write it here before this. So scale df dot drop. What do we want to drop? We want to drop the column which is clusters, right? Can I write like this? No, because I have to provide the axis also. The axis should be 1. That is, we are trying to remove the column. Now this will remove your clusters column, but only for this view. It will not remove it permanently. After this, if you see your scale df, it will still have clusters. If you see, it will still have clusters. So what I should do is I should set in place is equals to true here, so that your clusters column is removed permanently. So now let's see. Yeah. So from your scale df, your column is your clusters column is removed permanently. So now we can do the fit for our scale df. Then we can figure out what the inertia is. So maybe let's first print I value, print I. Then we print k means dot inertia. Okay. And then what we want to just do is in the inertia list, we just append the inertia value, which is basically this, and it's written like this, right? If you see here, so we append it here, and then finally in our inertia list we will have all the inertias, and then we can draw the, because we have all the inertias, we can draw the graph between inertia and the number of columns, number of clusters, not columns. So if you see, one second, there's something wrong. Yes, now you're able to see it, right? So for 1, the inertia is this. For 2, the inertia is this. For 3, the inertia is this, right? Now, if you just see your inertia list, so it will have all the inertia stored. So basically the first inertia was what? The first inertia, okay, this is behaving a bit weird. 1 second. So the first inertia value that we had was 2869 and then 2302. So if you see 2869, 2302, so all the inertias are now stored. Now if you see, as the number of clusters are increasing, the inertia is decreasing. But we want an optimal value where which is basically on the elbow, right? So that the inertia is also less and the number of clusters are also less. So now what we will do is we will draw the graph. Okay. So on the y-axis we have inertia. On the x-axis, what do we want? We want the number of clusters, right? Number of clusters. And what will be the number of clusters for us? It is going to be from 1 to 15. So it will basically be from the range 1 to 16 because 16 will not be included. So if you see your number of clusters, your range is 1 to 16. That is 1, 2, 3, 4, 5, 6 till 15. Now what we will do? We will draw the plot. And on the x-axis, we want these number of clusters. On the y-axis, what do we want? We want our inertia. So now if you see, the curve looks like this, and here we have the elbow points, right? Now, one more important thing. We don't know what is on the x-axis and what is on the y-axis, right? So we should provide the labels as well. So plt dot x label, it's basically the number of clusters, and then we have y label, it is basically inertia, and let's give the title also, elbow curve. Now we can set basically wherever there is a point, we can set it with a O or a dot. So here I can provide the marker also. So the marker is this. Okay. So now we'll get dots wherever the point is. Okay. So if you see somewhere here, we will have the optimal value of k. Now since here we are making it for multiple k values, let's try to zoom in this one, basically this place that is from 2 to 10 where we actually have the elbow, right? Obviously now if you see from after, so if you see 8, 9, 10, 11, 12, 13, 14 and so on, basically the inertia decrease is less. So but here if you see here we will have a optimal value of k. So maybe let's, instead of doing it from 1 to 16, let's try to do it from 1 to 11. That is basically have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then basically have these 10 inertias. Then the number of clusters would be 1 to 10, and then like this. So now if you see the optimal number of clusters, it will be clearly visible. The optimal number of clusters would be from, it will be here, 3, 4, that's the optimal number of clusters. 3, 4, okay? 3, 4. Okay, so that's the optimal number of clusters. So those clusters should be taken. We could take 3 also because if you see from 3 to 4, there is decrease in inertia, but it is less. So you can either take 3 or 4. It's totally up to you. Okay, that's how we find the optimal value of k, and then we can perform our clustering. So now with this k, let's say k is equals to 3, we will perform our clustering again. So what we will do is we'll say we are going to call our k-means and we'll say that the number of clusters that we have are 3. So here we'll say it as 3. Let's try to do it. So let's see k-means, and we provide the number of clusters as 3, and then we write k-means. K-means is the variable. Then what we do is we fit this on our data frame, which is scaled df, and then we make the predictions. So this is how, if you see now, our number of clusters are 3. So basically, points belong to either 0 cluster or 1 cluster or 2 cluster. So 0, 1, 2, and so on. So this is all about clustering, right? So each point will have either it will belong to 0 cluster or 1 cluster or 2 cluster. Okay, so this is unsupervised learning technique in which we don't have a target to predict, but we are just grouping the data into some categories. Now, let's move ahead. Let's move to the next algorithm, which is basically principal component analysis. Now, in principal component analysis, what do? Is we reduce the number of features. In clustering, we were grouping the data into a few categories or clusters. And in principal component analysis, what are we going to do? We are actually going to figure out, basically reduce the number of features, that is do dimensionality reduction. Now let's see our DF. Let's take our data frame back. So now we have gender, SSCP, SSCB, and so on till status and salary. So now what we want to do is we want to reduce the number of features, only the number of independent features. So we should not basically take status and salary into PCA because those are our targets, right? So what essentially happens in PCA is, so first you have independent attributes. The number of independent attributes are high. Let's say we have 10,000 independent attributes and then one target attribute. Okay. Then what do? Is you apply PCA and then what do is you convert these 10,000 attributes to, let's say you reduce them to 100 independent attributes and you still have your one target attribute. And then with this data, you perform the next model, that actual model that you want to build, let's say linear regression or logistic regression. So we don't want our status and salary, which are our targets, to be a part of PCA. We don't want to actually do the dimensionality reduction on them. So we are going to remove them. So what we will do is df dot drop, and the columns that we want to drop are basically status and salary, and our columns that we have to drop the column, so it will be axis is equals to 1. So in this way we drop our status and salary, right? We drop our status and salary, and now this is the data, these are the features that we want to reduce, right? Let's probably write it in another data frame, which is, let's say, new df. Okay, now let's see our new df. So now we don't have our status and salary. Now again, we would like to do the transformation, that is we want to standardize, because in PCA also we have the first step. In PCA, can we recall the 5 steps? The first step in PCA is standardization, right? Second step is find out the covariance matrix. Third is find the principal components or the eigenvectors and the eigenvalues. The fourth step is to draw the feature matrix. And the fifth step is to recast your data on these principal components in the directions, in these directions of eigenvectors. Okay. So first thing is standardization. So we would like to do the standardization first. Okay. So again, we don't need to import it again and again. It's already imported above, but because I want you to write complete code of a particular model, that's why I'm writing this again and again. And it would be great if you can also write the code together with me, so that you also create this Jupyter notebook or Google Colab. I'm doing it in Google Colab. You can do it on Jupyter notebook also. But if you do it with me, you will also have this ready and you can write this as a project in your resume. So from sklearn dot, now where is standard scaler coming from? It is coming from pre-processing. And then we import standard scaler. Okay, and then we call the standard scaler. Okay, where is our linear regression coming from? Linear model. Where is our logistic regression coming from? Linear model. Where is our standard scaler coming from? Pre-processing. Where is our clustering coming from? Cluster. Where is our PCA coming from? Decomposition. It will come from sklearn.decomposition that we will see in some time. So now what we have to do is basically do the transformation on our new DF that we have. Okay. And it is going to give us arrays. It is going to give us 2D array. Okay. Now what we will do is we are going to call our PCA from sklearn.decomposition. From sklearn.decomposition, import PCA. Let's see if the spelling is correct. Let's see. Let's try to run this. Yes. Now basically you call your PCA and you have to tell the number of principal components that you need. Let's say I want 4 principal components. So I will say number of components is equals to 4. Now what would be it when you just say PCA and you don't specify the number of components? What will happen? Any idea? Here we are saying that the number of principal components that we need is 4. So whatever are the initial features, I just want at the end, I want 4 principal components. That is, I want to have only 4 independent attributes after I'm done with PCA. Okay. And if number of components is not set at all, then all the components will be kept. That is, if you have 10 features, you will get the 10 principal components. So you're not reducing the dimensions. But if you want to reduce the dimensions, then you should set the number of components to whatever number of dimensions you need. So let's say I want 4 principal components, and then I can store it in PCA variable. Now, what do I do? N components. It's N components, not N component. Okay. Now, again, what I have to do is I have to take this this array. This is the transformed array, and then basically do the PCA on that. So this is the data, the standardized data that we want to provide. You can directly provide the array as well. So here we will say PCA dot, and the function that we are going to use here is fit transform. Now, what will fit do and what will transform do? That's the question. So what do you think fit is going to do? Any idea? So fit is basically going to find the principal components for you, and the transform is actually going to reorient your data. Okay, so if we use fit transform together, both the things will be done in the same step. Okay, so that's what fit transform is. So at many places we have seen this fit transform. So fit basically figures out something and transform actually does the transformation. So fit transform method is basically the combination of fit method and transform method. And this method simultaneously performs fit and transform operations on the data, and it converts the data points. Okay. Now, let's provide the data that we have. Now, what is the data that we want to provide? We can provide this data, the standardized data that we have. So these are the four. This is basically how the data looks like after it's converted into the four new features, that is the four principal components. So our data is also recasted. Okay. Now, what do we do next? Obviously, this is not the data that can be consumed directly. So we need to convert it into the data frame back, right? So we'll do it. But before that, let's see how much information or how much variance is contained in each of the principal components. So let's see that. So if we say PCA dot explained variance ratio. So this will tell us how much information is stored in each principal component. So the first principal component stores 21.9% information, that's around 22% information. The second one stores around 15% information. The third one stores around 12.7% information, and the fourth one stores around 10.7% information. So if you see the total of this is the array. How can you sum it up? Can you tell me how can you sum it up? Can I just say sum like this? Yes, I can say that. So 60.9% of the information is stored in the first four principal components. So if you see, we had so many features, but in the first four principal components only, we are able to store 60% information of the data. If you need 80%, 90%, you just probably need to add a few more components. Okay. So if you don't set the number of components, then all the components will be taken. That is, all if the number of features initially are 10, then 10 principal components would be there. And if you do the PCA dot explain variance ratio dot sum, then you'll get it 1, because all the information is there in all the information is obviously there together in all the principal components. But that does not make sense because you're not doing dimensionality reduction. Okay. Now what do we do is we make a new data frame, and in that the data that we will have is basically this reoriented data that we have got from PCA. That is the data of the first four principal components. So let me call it as PCA array. Okay. So now if you see, now it will be in the form of a data frame. We already know that these principal components that we get, they are basically the linear combination of initial variables, but also they are less interpretable. We don't know what they exactly mean. And if we want to set the column names, we can set that as well. Columns is equals to PC1, PC2, PC3. Okay, we have to put the quotes. PC2, PC3, PC4. Okay, so now we basically have the data with us, and now in this new data we can append our targets, which are the status and the salary. Now if you see here, the indices are from 0, 1, 2, 3 till 204, and if you see your DF, the indices are 0, 1 till 214, because here we have removed some row records in the middle, because if they were outliers, we just remove them, right? So we cannot directly say that take the status column from here and put it here in this data frame. In this data frame, let me call this data frame as PCADF. Okay, let me just show you what I'm trying to say. If I say PCADF and I want to put another column, say status, and I just say that it's going to be equals to DF status, like this, what would happen? Any idea what has happened? Let me do it for salary also. Now you see your PCADF like this. And now if you see the info for it, do you see that only 196 of them are non-null? That is, we have some nulls with us. Okay, let me just probably see the head and if I'm able to show you some uh, nulls. Not able to show, but in the info you are able to see that there are some nulls. What has happened essentially is that the the indices for status and salary and the indices for the new DF or the PCA DF, they were different, right? So now if I have to check PCA DF indices, let's see, we have 0, 1, 2, 3 till 204. Whereas if you see your DF, the indices are from 0 till 214, right? From 0, they are there till 214. So what you essentially need to do is you need to reset the indices for your DF. You need to reset your indices. So if you do reset index, what would happen now? It will be in the same index, which is 0, 1, 2 till 204. And then from here, now you can take your status. Sorry, the status spelling. So now this is something that you can put here. We are getting the nulls because the indices for both of them are different. And then you do the same for your salary. Okay, now if you see the info for it, now there are no nulls. Okay, so basically when you're trying to add columns, the indices should be the same. If they are not the same, then you might end up with nulls. So that's why we have to put have both of the column which you're taking, it should have the same indices as the data frame where you're trying to insert that column. So now we have all non-nulls. So there is no null at all. Okay. So now on this data, let's try to do linear regression. Okay. So again, where do we import our linear regression from? We have already imported it above when we were doing linear regression, but since we want to write the complete models, and I'll be writing it again here. So from sklearn dot linear model, import linear regression, and then basically call linear regression and store it in a variable, invoke linear regression. Okay. Now the next thing that we will do is find out our x and y, right? So if you see your PCADF, what would be your x? X would be PC1, PC2, PC3, and PC4. So x is basically df dot ilog, you take all the records and you just take the first four columns. So basically take from 0 and you take 0, 1, 2, 3. So basically it has to be 4. Okay, because you have to take 0, 1, 2, and 3. And now this will be your 2D array. Sorry, 2D column, 2D data frame, or you can say just data frame. And if you take the values of it, it's going to be a array. So when you take the values, you'll get a 2D array. This itself is obviously going to be the data frame. Why it will only be the data frame? Because you're just selecting the records and the columns. It will still be a data frame, and then after converting the data frame into an array by values, you'll get the 2D array. Okay. Now moving ahead. Okay. Now one more thing. We are not taking DF. We have to take PCA DF because that's the new data frame that we have, right? So now this is the data frame. We have already taken care of standardization in PCA, so we don't need to do it again. Then we have to take our Y also, which will be a 1D array. So first you have to take the column, which is the column that you need. It's the salary column. So Y is equals to DF. You can take the salary column as it is and convert it into values. So now you have your 2D array and 1D array. Okay. Now the next step, basically do the train test split. So where does the train test split come from? It comes from sklearn dot model selection. Let's see. Yes. Import train test split. Okay. And now what you have to do is basically figure out, basically do the train test split for your X and Y. So we call train test split, and then we provide our X and Y. We also provide the test size. Let's provide the same test size as we did earlier, which is probably 0.3. And then we put the random state also to be some value, let's say 42. So basically what we are doing is we are saying that the testing data should be 30%, the training should be 70%. And we already know the importance of random state, because if we set the random state, no matter how many times we run the train test bit or the linear regression model, we are going to get the same training and the testing data, and that's why we are going to get the same evaluation metrics. Now this will be stored in 4 variables, which are xtrain. Then the next one should be xtest, then ytrain, and then ytest. So now we have our data. Xtrain would be a 2D array, xtest will also be a 2D array, ytrain will be a 1D array, and ytest will be a 1D array. Okay. Now, once we have done the train test split, now we need to do linear regression. So basically, we build the model, that is, we call the fit method and provide our xtrain and ytrain. And now this is going to build the model for us, and internally it uses a variant of stochastic gradient regressor. And then it is going to, now it has built the model. Now we are going to make the predictions on the X test. And then we are going to compare these predictions that we have with our Y test, that is the salaries that we already know of. So let's say these are Y pred, and then we are going to find the R score. So from sklearn dot metrics, okay, so we can write it as from sklearn import metrics, and then we can write metrics dot R2 score, and we can provide our Y test and Y pred. So we are getting 31.5%, whereas obviously when you did the linear regression above, let's see, you were getting a better accuracy. So have we compromised our R score? Yes, we have. Let's see how much. Let me see where is linear regression. Yes, here is linear regression, and let's see what the R2 score we were getting, R square or coefficient of determination. We were getting it as 76%. Now, if you see with four principal components, we are getting only 31%. So either we should increase the number of components, and obviously we are getting it 31%. The reason is we have only taken 60% information of the data. So we either should increase the number of principal components, then only we'll be able to reach somewhat at par with what we were getting from linear regression, because we are just capturing 60% information of the data and 40% information of the data is lost. So we should ensure that we are able to capture some 80, 85 or 90% of the information. Then only our results that we get after doing PC and then building the model, they would be at power or maybe a bit less than what we had without PCA. But PCA is obviously a trade-off that we do between simplicity and accuracy. So we are going to stop here, and that was all about that we had in the course. So we started off with Python. We discussed NumPy, Pandas, Matplotlib, Seaborn, and then we moved to the machine learning terminologies and jargons, and we understood a lot of things like outliers, pre-processing, label encoding, one-hot encoding, so many things. We also studied a lot of graphs or visualization techniques like heat map, box plot, which are so important for data analysis. Then after that, we moved to models. We obviously first understood that there are three categories of models: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, what do we have is we have label data. Let me just draw it. Supervised learning, we have labeled data, and in that we studied two categories, classification and regression, and we implemented both of them in our data set. Then we studied unsupervised learning, two things that we studied. Obviously, there are multiple techniques, but we studied two, which is clustering and PCA. And the last one is reinforcement learning, which we just touch based. So we studied variants of supervised and unsupervised learning. And we understood the basics of it. We understood the theory, we understood the mathematics, and we also understood how do we implement those in sklearn. sklearn is a very, very powerful library that Python has, which helps us in pre-processing and model building. So that was all about this course. Now, a few things that I would like to add here. So machine learning is a wide field. Data analysis is very wide. There are lots and lots of job opportunities that you get in data analytics, you get in machine learning, you get it in artificial intelligence, you get it in deep learning. So there are lots and lots of job opportunities around. So if you feel that this all was exciting for you and you're interested, do go ahead and keep on reading about new models, trying to implement new models, trying to learn more and more about machine learning, artificial intelligence, and deep learning. Here we covered the basics of data analysis and machine learning, but there are lots and lots of models. There's a lot and lot of research going on multiple models. So if you're interested, try to go ahead and learn a few models on your own. Try to pick up some data sets, and then try to do the data analysis, model building, and basically write a proper report on that data analysis that you did. Even for this that we did, for this Google Colab, try to write a report on whatever your findings were and whatever models you built and whatever you learned from. Also, there are multiple projects that you can do. You can pick up one simple project, let's say movie recommender system, and try to implement the movie recommender system. And in this process, you're going to learn a lot. So this is just the start, but there's lots that you can do in data analysis. So go ahead and actually take up some data, analyze it, build models on that, or take up a project like movie recommender and then try to uh, implement it and understand and learn. And obviously, in this way, the more projects that you do, the better it would be for you, because you'll be able to write them in your resume. So that's all for this course, and feel free to reach out to me for any questions. Thank you.